Hello everyone, welcome to the fourth session of our computer science module. For today's agenda, we'll be exploring further on search algorithms. We'll be looking deeper into the types and into different forms of search algorithms, why they're so important, and we'll be exploring different practical applications of search algorithms. Where all are they exactly implemented? Why they are so important to certain systems, to certain real life applications, and so before going in depth of the types of search algorithms, let's just first explore what exactly is meant by the terminology search algorithm. So basically, search algorithms are basically algorithms powered by artificial intelligence that is used to find specific data points within a large database, or to put it into simple terms, they're basically used to find a specific data in a large huge collection of various data points. On this note, we'll be diving deeper into our first type, which is basically our breadth first search. So basically, to begin with, the breadth first search is one of the most fundamental search algorithms which is used in CS, or computer science, and artificial intelligence. The breadth first search algorithm is designed to explore a graph or a tree, which you can see in the image over here, by basically visiting nodes horizontally. So what I mean by horizontally, basically it goes level by level, and so it starts from a chosen starting node. So to give you a practical experience, our starting node here is A. This A is our starting node. Instead of going deep into one branch, so instead of going from A to B to D, it basically first explores all of the nodes that are directly connected to the starting node, and after finishing that specific level, it moves on to the next level. So what I mean by that is, so basically you have node A over here. So now we can see that B is directly connected to node A. So it goes to B, and it does not pass on to the next level until all of the nodes that share the same level as B are explored. So this is basically marked as visited. And the thing with breadth first search algorithms is that all of the other nodes which are still yet to be explored, they're basically put in a queue, which helps the algorithm to keep track of all of the nodes that are still yet to be visited. So basically, as the process continues, like I've said before, it explores all nodes and layers. Because of the structured approach, this type of algorithm is particularly useful when we want to find the shortest possible path in an unweighted graph. Since the first time the algorithm reaches a goal node, it is guaranteed to have found the shortest possible path in terms of the number of steps. So basically, in terms of its application, it is widely used in many areas of computing, such as network analysis, pathfinding problems, and exploring connections in large data sets. Now we'll be moving on with depth first search, which in fact is the opposite of our breadth first search. So basically, unlike breadth first search, which explores your nodes A, B, C, D, E, F, G, layer by layer, depth first search basically goes branch by branch. It goes and explores one branch as deeply as possible before moving on to another branch. So basically, we have now 0 over here as a starting node. So it basically goes on to 1 and 4. It goes into one specific branch as deep as possible until the search algorithm reaches the very bottom or the last node of a particular branch. So the algorithm starts at a chosen node and it moves on to its connected neighbor. From there, it basically goes travels deeper, as deep as possible. Um, basically and it essentially repeats this process until it reaches a node where it can no longer further explore the remaining neighbors. So at that point, the algorithm backtracks to the previous node. So you've got from 4 backtracks to 1, and basically this process continues until the goal node is found or all nodes have basically been explored. This type of algorithm is often implemented using stacked data structure or regression, which naturally supports the deep exploration process and the backtracking process. So this takes us to or a search A algorithm. So basically, this algorithm is used to find the most efficient path from a starting node to a goal node. Basically, so your starting node in this case is 7. Your goal node can uh, would be zero. It could be anything within this diagram. So it basically works by evaluating each of the possible nodes, like using two values, your gn and your hn. So we'll start with gn. It basically represents the actual cost from the starting node to the next node it basically explores. That is your gn to the current node basically. And your hn is basically, your hn represents the heuristic value. So what exactly the heuristic value is, you may ask. It basically, it is a value that determines or approximates the total cost or the distance between the current node, and the goal node basically. So basically these values are combined into a function. So this function is fn is equal to gn plus hn. And so basically this helps this type of algorithm to decide which node to explore next. So at each step of the way, this type of algorithm selects a node with the lowest fn value, meaning it chooses a value that is cheap and that is low cost, um, essentially in terms of going from the starting node to the current node. And it also selects a cheap path in terms of the distance, in terms of the proximity between the current node and the goal node. So by balancing the real cost and the estimated distance, so this type of node is able to efficiently, this type of algorithm, sorry, is able to efficiently search through possible paths and often finds the most optimal solution, the cheapest and the most efficient solution, while exploring basically fewer amount of nodes. Fewer amount of nodes compared to the number of nodes that other types of algorithms would explore, which we would further explore and cover in this session. So now let's move on to uniform cost. So basically, the uniform cost search is a search algorithm that is used to find the lowest cost, the most efficient path between the starting node, which is in this diagram, which is S, to your goal node. So it offers the cheapest path, it offers the most efficient path. So instead of exploring node based on the level, horizontally or vertically, the algorithm basically selects the node with the smallest total cost from the start. So basically, to from the very start, it basically selects the neighboring node, given how cheap it is in terms of its cost. It uses a priority queue to keep track of which node next has the lowest cost, and which node should be explored next based on how cheap it is in terms of its cost. So this process continues, it repeats until the goal node is reached. So because the algorithm always expands with the least expensive path, it is known to be a very cheap and a very cost efficient algorithm, and it basically guarantees finding the optimal solution when all when all path costs are essentially positive. So now let's move on to greedy best search. So this is a type of a search algorithm that focuses on reaching the goal as quickly as possible by using a heuristic approach, like we've discussed earlier in this session. So unlike algorithms such as uniform cost search, which considers the total cost of the path so far, this type of algorithm, the greedy best first search, only considers an estimate of how close a node is to the goal, how basically its distance, its total cost from the current node to the goal node. So this estimate is again called a heuristic function, like we've discussed before, and it is usually represented as hn. The heuristic basically gives algorithm an idea of which node appears to be the most promising or the most cheapest at any given step of the way. So the algorithm basically begins at the starting node, which we've got A over here. It starts from A, and for each of the neighbor, the heuristic value is calculated to estimate the distance from the node to the goal. So the algorithm then chooses the node with the lowest heuristic value possible. So basically, from its neighbor, so you're supposing you're starting from A, it looks at BCD, and it basically identifies which of the node it is directly connected to, which of it offers the least heuristic value, basically the most optimal path to finding the goal node. So it basically it uses the function, it uses the heuristic function, and from there the process repeats. The algorithm evaluates the closest neighbor, the neighbors of the current node, and again selects its neighboring node, it's directly connected node that offers the least heuristic value. and this process basically keeps on repeating until the goal node is officially reached. So to manage which node should be explored next, the greedy best first search algorithm again uses the priority queue which we discussed before. It keeps track of which next neighboring node should be explored, that again offers the least amount of heuristic value. So the node with the smallest heuristic value is always explored first. This is this is the first and the foremost priority of this type of algorithm. And so because the algorithm always chooses what appears to be the most promising, most efficient path at the moment, it can often reach a goal very quickly, very efficiently, using the shortest path possible. So but the downside is, however, since the greedy best first search algorithm only considers the heuristic estimate and ignores the cost of the path already taken. So, to give you an example, it basically ignores your GN value. Basically, it is to remind you, it is basically the total cost from the initial node to the current node. Basically, it ignores GN completely. It ignores that part of the function. And so basically, because of this, it does not always offer you the most optimal solution or the most optimal pathway, given that it does not consider the total cost from the initial node to the current node, basically. And so because of this, in some cases it may follow a path that looks promising, like efficient basically initially, but it turns out to be longer, or it turns out to be more inefficient than it was initially planned, by the algorithm. So regardless, its speed and simplicity makes it useful in many scenarios and day-to-day situations, particularly in pathfinding and artificial intelligence problems, where quickly finding a solution can be more important, where basically the time taken by the solution, it is more essential, it is prioritized more than guaranteeing the shortest optimal solution possible in that given scenario. So this takes us to the end of the module. Thank you very much for sticking to the very end. I hope you've learned about the five types of algorithms that we've explored in depth today. What exactly are the objectives of these search algorithms and how they are used in our AI tools today in finding, in optimizing various different solution pathways, and how they are essentially leveraged and utilized to find the most efficient solution possible. Uh, so, on this note, we hope you've learned quite a lot today, and we'll be meeting you in the next session.